Have we started?
Yes.
Yeah. Okay. Okay. Thanks for coming along. Just to let you know, we're going to give it a couple more minutes, just for a few more people to join, and then we will then we'll crack on. Okay, so we'll get underway. We'll get underway now. Just some housekeeping. Cameras and microphones are switched off, and any questions throughout the presentation, if you could please put them in the Q&A section, that would be much appreciated. And then, yeah, so, okay, so let's begin. So my name is Matt Day. I'm the sales manager for Dolphytech for UK, Europe, and we also take care of our Middle East and Asia Pacific partners as well, and some of our customers in those regions. Presenting with me today is Sam Conway-Wallace, our application specialist, and we also have another Sam, Sam McLennan, who is just looking after us today to make sure that everything works all right. So anyway, so let's begin. Bringing defects into focus with advanced techniques. So this is a webinar that is centered around our newest software technology that we're bringing to market. And to cover discussing over the next 45-ish minutes is, first of all, we're going to have a brief introduction to our technology and sequencing before we move into C-scan beamforming, the focus of our webinar today. C-scan beamforming is also known as ARCUS. And then from there, we'll move over to Sam Conway-Wallace, who will give a live demonstration before we close and move into any Q&As that are available. Okay. So, a little bit about Dolphytech is that we have a global presence that is organized through 3 core office locations. Our head office based in Oslo, Norway, and then we have 2 satellite entities, one in the UK and the other one in the USA. We have a network of partners. Our partners total around about 30 now, and they help us to reach all corners of the world. Dolphytech was established in 2009 in Norway, and since then we've become an established solution provider. We're recognized by organizations. The 2 largest institutes for non-destructive testing are their ASNT and BINDT, but we're recognized throughout the world through different organizations. The latest one to our arsenal is Lloyd's Register for Marine, where we were able to validate our matrix array technology as a comparable and comparative technology to the incumbent phased array and standard ultrasonics. This isn't an exhaustive list, but a little bit about our customer base, our client base, is that this is really sort of segregated into 4 areas. Top left, space. So we do a lot with sort of space research and manufacturing. Top right, we enjoy quite a wide portfolio of commercial airlines. Moving to the bottom left, we've got some high-end automotive customers, as well as some defense companies. Now, we are limited in the companies that we can share, but there's some interesting names down there. And then on the bottom right, we see quite a spread of education, research and development entities, that kind of thing. So we have quite a wide portfolio of clients across the globe. Now, moving into our technology and scanning sequence. So the evolution of ultrasound. Everybody is familiar, or should be familiar, that conventional ultrasound is where all this began. Just a single element transducer, pulse in a single A scan for you to be able to determine thickness, defects, that kind of stuff. Industry then took a leap forward with the invention of phased array ultrasound technology, where they were then able to manipulate and manage A scans from multiple elements to be able to produce a cross-section view, and with encoding almost a 3-dimensional view on the system. And that was a huge leap forward, and really sort of put ultrasonics on the map. Then 2009 along came matrix array. So matrix array ultrasound took what we already know from A scans and phased array in compression, and made it into a volumetric data set. So not only do you get 1 B scan, you get 2 B scans, an A scan, and C scans, and a 3-dimensional render, all within the same footprint, transducer footprint. Looking inside our transducer, how does it actually work? So we have the same sort of physical conditions in the fact that we have backing material, piezoelectric material, and a method of coupling. What differs with matrix array is that instead of a hardwired piezoelectric material, like a ceramic, we use a polymer-based piezoelectric material, and we use transmitting and receiving electrodes in order to generate our ultrasonic waves and then the corresponding ultrasonic data points for the returning signals. In essence, how we do that is everywhere that the transmitting and receiving electrodes intersect or cross is where we ultimately generate an ultrasonic A-scan data point. So how does it look? So when we're emitting sound, we actually emit on a column of sound. So you can see there from the animation that we create a column wave going through. Now, our electrodes are fixed in voltage. So in order to get deeper penetration, we are then able to activate an increasing number of transmitting electrodes in order to achieve more penetration within the material, the subject material. If we then now take a look at what the how the transducer is made up, so this is using our higher frequency transducer, which has 128 electrodes transmitting and 128 electrodes on the receiving side. So it's quite a unique row column array design. It harks from the medical application of being able to of ultrasound generation, an image generation, should I say. And what we're doing is we're transmitting on 128 columns. The aperture height, so the size of the transducer, is 32 millimeters in length. And then we've got our receiving electrodes as well. So again, 128, and they are 32 millimeters wide as well. So what we're doing is at any one time during live capture, we're capturing hundreds of millions of data points each second. This corresponds to being able to display 16,384 A-scan data points within the footprint of the transducer. All of our ultrasonic electronics are housed within the transducer. So to increase the signal to noise and to give us the best possible signals is the closer the ultrasonic electronics are to the surface, the better. So for us, they're right next to it. They're right next to the surface of inspection. But it's not just a simple case of transmitting sound and listening to sound. What we actually do is we do a thing called multiplexing. So if we imagine that the blue line is a transmitting electrode and the green lines are the receiving electrodes. So in this instance, we're using the low frequency transducer, which has 32 elements in each direction. And as we're scanning, the probe is firing on all of the columns, and it's listening in a fixed pattern across all of the receiving electrodes. Now, once it's done a single pass, that's typically 1 frame rate per second. Okay, and what that ultimately allows us to do is then we can operate at, typically we can go up to 30 frame rates per second. So once the transmitting electrodes have all been activated and all of the receiving electrodes have been activated as well, that's 1 frame rate per second. And we can go up to 30 frame rates per second during live scanning. In real world applications, depending on the part, depending on the material, a typical type of application, we would be looking at somewhere between 12 to 15 frame rates per second. And at that rate, we would, the operator it's almost impossible to separate the hand movement from the screen display and the resolution. So it's as live as possible. Excuse me. Okay, so, but what does it actually look like? That sounds fantastic, but what are you actually seeing on the screen? So bottom left, we have a short video. Excuse me. So on the bottom left, we have a short video that shows the screen resolution and the screen display. But what are we actually seeing? So we have our B scans, horizontal and vertical. These are a cross-section area of the C-scan display, and these are generated anywhere that this vertical and horizontal lines are generated. So you can move them around the screen, you can move it in live, and you can move it in analysis mode, and it gives a real-time cross-section area view. Where they intersect, that's where we generate the A-scan data from. So again, anywhere you place those two lines, and that cross point will give the corresponding A-scan data. Then, of course, we've got our C-scans. So our C-scans are, we have 2 on the view here. The left in grey, that's looking at amplitude, so the amount of sound returning back to the probe. And then on the right, we have time of flight, so how far that sound is traveling. And then, of course, we have our 3-dimensional render. You'll see it on the video as it's being displayed here. The 3-dimensional render is a live render. So as you move the transducer, it is also moving and updating as well. no measurement can be performed on the 3D render, but it's there as a visual confirmation. It's also extremely useful for reports. It's also extremely useful for people who might not be skilled and trained in NDT. It's a lot easier to understand what a crack or a delamination looks like using the 3D render than it is trying to convey it through the traditional A-scan data as well. On board, you get statistical information. So you get statistical measurement panels that give things like mean, median, and mode over the area that falls within that circle. And you also get a histogram view, so you can see how your signals are being distributed. And then on the bottom right-hand corner of the video, you can see the live 3D render moving as the image moves for the equipment. And again, with the 3D render, you can flip it, rotate it, zoom in, zoom out, that kind of stuff. Okay. So that's the equipment. That's what it looks like. But a little bit about Dolphytech. What do we stand for? I shan't read this verbatim, but ultimately we put the customer first. So we do a lot of innovation projects with customers, but ultimately we want to get people inspecting their parts as fast as possible. So our menu design is simplified. It's very efficient, and also the equipment is extremely efficient as well. So you can have from out of box to scanning in under a minute. So when time really matters, that's quite an important measure. We're more than just a off-the-shelf tool in the fact that Dolphytech owns the IP for all of our equipment. Everything is designed and built in-house, and we have the ability to quickly develop new software, develop new tools. I should say, as a caveat, we are a commercial company, so these are normally paid for projects, but ultimately we can work very quickly and we can deliver products directly to the customer. Okay, so that's the instrument, that's the technology. So now, back in 2009, when the Dolphycam 1 was originally conceived and we brought out the 2D matrix array, that was revolutionary in its own way. But then very quickly we moved into B-scan forming, so beam forming. So this is a way to correct the signals for angle sensitivity and time shift as well, so that you can actually pick out defects that might ordinarily be missed. It was a really great example of the technology. The reason why it was B scans only at the time was due to the availability of technology that was common out in the marketplace. So it came as standard on the instrument, and it was a useful tool for analysis, if anything. So, but it was a proof of concept. It's something that we could evidence that was able to be done. So whether you're looking at on this image here, the crosshairs are fixed on a flat bottom hole, but at the top you can see the difference between a rounded hole. So on the left, you just about see the deformation of the ultrasound, but on the right hand side, it can actually zero in and focus in on that tip of that sphere, a spherical hole. From then, we were able to very quickly develop C-scan, but again, we were at the mercy of of industry and the available technology. So since then, industry has caught up. The available computer processing now on the market is such to a point that we're able to release this software. So ARCUS, what is it? ARCUS does everything that the B-scan did, but now displays it in a C-scan image. So when we first conceived this, it was looking at 30+ minutes in order to process the data. Now we're up to 10 seconds. So this is something that can be done, in your offices on your own hardware. It's important to point out that there is no AI involved in anything that you see here. This is pure mathematics, and the volume of mathematics is staggering. So the last line there, it can be used live or on stored data. This is something I think that will be better visualized with Sam when he takes over for the demonstration. But ultimately, once you find a defect or you find an area, you can then pause the probe, and the system will kick in and process the data. So the image that we're looking at there is on a Perspex rose. So it's a small step wedge in circular area. And on the left, using a 2.5 megahertz transducer, it's got 128 electrodes transmitting and 128 electrodes receiving. And what we're seeing here is the result of 16,384 data points. We then apply ARCUS as a post-process. You can see the image is a lot clearer. And we're actually able to pick up anomalies within the Perspex that you can't see visually, and the system might, and traditional ultrasonics don't pick up. And we're looking at this little section here. This is within the composite, within the Perspex itself. So we get a far clearer, a lot more detail, and a far better resolution. So how does it work? Well, ARCUS is the short version, but it actually stands for Advanced Row Column Ultrasonic Synthesis. What we're looking at, each pixel that we're looking at on the screen is the result of echoes. So single point in the material that's reflecting sound back to the transducer. What ARCUS is doing is that it is aligning and weighting the signals, and it's combining those signals. We're then able to scale that to the three-dimensional view, so X and Y and Z as distance, with ARCUS. At any one time within the probe area, we're performing just above 268 billion calculations per pixel. So that sort of lends a little bit of weight as to how we were able to do this a lot longer before we were able to bring it to market. But what's happening with the ultrasound inside? So with every ultrasonic wave, we get our reflection between every medium, and every time it goes through a medium or an interface, we see a reflection coming back. We know that. Items B and C there is typically data that we wouldn't naturally record or display on the instrument. That's sound that might be reflected from each interface, or with every interface, you also get scattering as well. So a lot of the ultrasonic data is lost within the part. So what ARCUS does is that it takes all of those signals and it realigns them back into the position that they should have been. So seeing it work on a rose is great. It's a homogeneous material. It's a single material. But what happens when you look at multiple materials like composites? So if we take this application here, so we're looking at a honeycomb structure. This is a aluminium honeycomb. Pre-ARCUS, so this is what we're looking at. On the left-hand side, you see those white spots. They're the high amplitude concentrations, and they come from the center of each of those cells. But with ARCUS, we can now see the cell wall structure. We can see the individual shapes. We can also see the areas where foam might be bonded to the area and how they interact with the cell wall structure as well. If we look at something like a delamination from impact, this is a monolithic carbon fiber panel, and it's been subjected to an impact damage. So on the left-hand side, we've got that there. And then post-ARCUS, the biggest improvements are in the B-scans, and also the being able to pick out the edges of each of these delaminated areas as well. It also aligns the amplitude as well. So actually, we're not seeing these high amplitude areas in white. We're actually seeing a lot more, a more uniform data set as well. How long does it take to process? So just to give you an idea, so switching the process on, calculates it twice, and then all of a sudden there it is. You've got that data processed as well. This is a thin-skinned carbon fiber skin bonded to Nomex core. It's been subjected to a drop test, and common factor is when you have the impact area, you get an area full of couplant, and that can help to deform the B-scan images. Look at it post-process in ARCUS, and while you see a much more improved distribution in the C-scan, you also get far clear segregation in the B-scans as well. So again, from a research and development perspective, this is an incredibly valuable tool. Okay, so this is the point where I pause, and I'm going to pass the baton over to Sam. Sam's going to give a real-time demonstration on, I think, 2 samples, just to give just to prove what we're saying, that this can be done on your own hardware. Okay, so Sam, over to you.
Cheers, thank you, Matt. Hello, everybody. Hopefully you can see my screen. What I'm going to demonstrate to you today, I've already set up the basic settings. What I've got in front of me are 2 carbon fiber samples. Hopefully you can see the flat bottom hole in the bottom. We often use flat bottom holes because they are very good at representing the delaminations that we commonly come across in our carbon fiber panels. So the first thing we're going to do, this is in the normal setting without ARCUS. So you can see on my screen we've got our live C scan, and where these lines intersect you can see the representative B scans. Where these lines cross is our A scan. If I turn on the probe, you can see on the top I'm green, so at the moment we're paused. If I turn the probe on, that takes us to live view. So as I scan around the part, I'm going to be trying to find these flat bottom holes. As I rotate the probe through 360 degrees, you can see the ply orientation within the sample clearly defined. I've got a 2.5 megahertz probe fitted, and I've got the Aqualine delay line. So I'm going to scan towards my first flat bottom hole. So we can see the flat bottom hole, it's relatively clear. We can see other indications. We can see the change in amplitude or the change in the grayscale. So just remember that amplitude is our attenuation based inspection. So we're looking for those change in amplitudes. So the more gray is less energy. The brighter, the more white is more energy. So you can clearly see around the outside, this is our back wall, and then you can see the center of our floor. But I guess what we're trying to do is define the size and shape of that floor. So we can see in our B scan, we can see that we've got a reflector that's before the back wall in both of our B scans here. So if we wanted to, we could now floor size that using our circular measurement tool. And it's going to be a little bit of guesswork as to where the edge of that floor really is. So at the moment, it's not particularly well defined, but we can see a floor of some description. Now, if we enable ARCUS, so we'll come down to ARCUS, make sure we've got the right parameters selected, and then we just simply turn our ARCUS on. You can see at the top, it's going to run the calculations twice, and then you'll see the image will sharpen up. So straight away, you can see that we've got a much more defined circular floor, which will allow us to floor size more accurately. And I guess the idea is that 2 or 3 different inspectors are going to floor size that more accurately, closer to what the real floor is, rather than if we turn off ARCUS, somebody might decide that the edge of the floor is there, somebody might decide it's here. So there'll be a range and a variation. Now, this sample that I'm using was subject to 100% vacuum. So it's the kind of reference standard, the good standard that we're going to compare from. I'm now going to go to the other sample that I've got in front of me, which was subject to 75% vacuum. The idea behind that was to try and simulate some type of porosity, some type of flaw in the manufacturing process. So again, we'll make a start. you can see straight away that amplitude is lower. If I just compare those two samples side by side, so my probe is half on the good sample or 100% vacuum, and then half on the poorer sample that's got more porosity. So you can see we've got a lower return because the sound is going into that sample, it's being attenuated by the porosity, and the sound is being scattered more, which means that when we come to the floor looks worse, and actually it might not be that well defined. So the floor is there in the center of the screen, but it's not particularly clear to see as compared to the good 100% sample. That's easy to see. And if you come to your porosity sample, it's not as well defined and it could be missed. So if we now apply ARCUS, we're going to place the crosshairs in the center to make sure we can see it in our B scans. And we're now going to turn ARCUS on. And this is going to do the calculations. So from my perspective, ARCUS seems to be able to see through the fog of the attenuation that you get in a poorer sample. So you can see now you've got an image that's almost as good as the reference sample, but this is in the sample that's got more porosity, that is more difficult to define. Now, the bonus with ARCUS is you don't have to do it on one TRM area. You can do it on a mapped area. At the moment, depending on the power of your PC, the one that I've got here, it's basically a gaming laptop, and you can do, we did 200 millimeters square, and that took about a minute and a half, not particularly long. If you had a more powerful system, that would be quicker. So that kind of defines how you would employ ARCUS from an applications perspective, the advantages that it brings from being able to define the floor slightly better to get you a slightly better accuracy on your measurements. It also defines it in your B scans. Everybody's been very quiet to now. Do we have any questions popping up in the Q&A?
Yes, I think there are some, and Sam Mac will run through those towards the end. And a good thing to point out here is that we're not just trying to do this on really easy defects to pick out that that might be in the middle of the sample or close to the surface. This is a near back wall defect or flat bottom hole. Sorry. Which again, I think as Sam has done a sterling job there of pointing out that in the live view, that could easily be missed. That could easily be caught up in the noise of the back wall signal. Having ARCUS as a post-process tool, and it is a tool. It's there to assist in the finding of defects and the sentencing of defects. Is that nobody is infallible. Everybody. You have to make a judgment call, and ARCUS is there to help you make that call and define those areas of interest. So yeah, I think that's a
good point, Matt. Thanks. So there was something else. So this can be done post-process. So here's an FMC data file from a curved glass fiber pipe with a floor just before the halfway point. So this was the raw data. This is the raw image. So we can see the floor. I know it's circular because I can see the other side of the sample, but represented in ultrasound, it doesn't look particularly circular. Again, applying ARCUS to this previously taken data set. So again, it can be done retrospectively to any data set that's been captured by Dolphicam. And then we apply that. So we can see that it's kind of highlighted and pinpointed that floor. It's made the floor more realistic, and it's kind of excluded the noise and attenuation you typically get from glass fiber pipes. So again, it can be used. It's just something in your toolkit to use to help you evaluate. I mean, from my perspective, this is quite clear in the B scan anyway. However, you could decide that you're going to apply ARCUS just to see if that floor is the actual size that you think it is, or if it can be better defined.
That's a great example, I think, of the way in which that you know, something as attenuative as glass fiber can, you know, potentially cause a defect to be oversized, you know, and certainly amongst the noise of all of those boundary layers within the material. Ah, great example. Great example. Okay. Thank you, Sam. I think it's worth to keep your set active just in case we need to answer any questions. But I'll take the baton back from yourself, if that's okay.
Over to you. Thanks, Matt.
Thank you. Okay, we can see this, yes? So, okay, so that was our...
Matt, you're muted.
Thank you very much. Sorry, yeah, just saw that. Yeah, so that was our demo. That was an excellent excellent view. Thanks so much, Sam. Now we're a little ahead of schedule, but hang on a second. And we all see our conclusion here.
Yes.
Yes, thank you. So yeah, I guess in conclusion and to wrap up this webinar is that we're not applying any sort of AI or artificial intelligence in any form to our calculations. The fact of the matter is that the DolphiCam generates an absolute ton of data. So our goal is to try and unlock as much of that value of A-scan data as feasibly possible. We are at any one time, in the traditional sense, making millions of calculations. Then once we apply our post-process ARCUS software, we're then moving into the billions of calculations. So the ultimate goal is to improve resolution as much as feasibly possible within a portable system. So not only do you get a live 3D, you also get an extremely powerful post-process system too. We've been 6 months in the making of this version of ARCUS. We originally started in a lab, and now when the software is due for release in the next couple of weeks, it will be an in-field device. So how have we achieved that? So our equipment will be spec'd in order to be able to manage it in the future. So we'll have dedicated GPUs, 64 gigabytes of RAM, and a 5080 graphics card as well. There will, in the portable side of things, there will, I think, be time constraints. But the beauty of the DolphiCam software is that that data can be transferred very easily if you're lucky enough to be able to use to have access to a cloud connection. We completely understand that some companies and some industries don't permit that, but data from DolphiCam 2 can be saved directly to a shared server on the cloud. And that means that other people within your organization can use the software in its standalone version and be able to perform this post-processing afterwards. As Sam demonstrated, is that you can then revisit previously saved data and perform the same process again as well. So we look forward to the time when this can be an in-field process, and currently we can offer it as a desk-based analysis software. So it's not really a motto, but ultimately it's a goal. Is the fact that at no point are we aiming to replace the human factor, but we certainly have turbocharged it. So we are, I think, actually pretty good on time, so we can take a couple of minutes to answer any questions. If anybody wants to reach out directly to me, by all means, scan the QR code. You'll get my contact information, and you can reach out to us directly with any questions. Just on one final closing point is that we enjoy showing these types of things on our samples and on samples that customers give to us. But ultimately, this is something that should benefit industry, and we actively are working with a number of key players across different industries in order to be able to make sure that this is applicable in the real world. So up until the point of release, we can discuss with you directly your application, and we can also provide 30-day demo licenses for you to test the system out as well. You have to have a Dolphycam, I should say, which is, so if you haven't got one, again, you're welcome to buy one. But then, of course, it can help us really sort of put this into industry and benefit everybody on a whole. So that's me. Thank you very much. And Sam, Mac, could you take a look at any questions, and we'll do our best to answer them.
Yep, so we got one in the chat that Sam answered, but might be good to just answer kind of so everyone else can hear. And if anyone else has any other questions, we have around 3 at the moment. Please do not hesitate to put them in the Q&A, and we'll get to them. So the first one was, does ARCUS work with our existing equipment, and is any other equipment required?
Sam, do you want to take that one?
Yeah, sure, absolutely. So yes, ARCUS does work with our existing equipment. We did have a Dolphycam 1, so it doesn't work with that one, but that's really old. So yeah, any DC2 or DC2 plus, if you've generated an FMC file, then you will be able to retrospectively apply ARCUS to your FMC files. Next question was, is any other equipment required? Not for ARCUS, no. There's no additional hardware. You would need a software update, and so long as your IT system, your laptop, your tablet, whatever it is you're running your software on, so long as that meets the minimum requirements to run ARCUS, then it's just a software update. If you've got a slightly less powerful machine, it's still possible, but it just takes a bit more time.
Great, thank you.
So we just had another one come in. So thanks for the presentation and demo. How would ARCUS behave when inspecting a defect that is not a perfect reflector, such as a FBH or a Teflon insert? Would part of the ultrasonic signal be reflected while the remaining portion is transmitted to produce a back wall echo? In that case, does ARCUS rely on TOF C-scan?
Yeah, I can take that one. So it's to be reminded that our system works compressional only, so we don't do any shear wave. So basically, it would run the calculation based on the floor that it sees. So at the moment, we're still testing and evaluating all the different floor types, the different floor mechanisms. So that's a really good question. I'm going to take that one. I'm going to put it into my matrix to go and test, but in effect it doesn't work on time of flight, it works on amplitude. So yes, it would sharpen up the time of flight image. It relies on the amplitude signal for the calculations.
Thank you for that. So next one is, can you still map with ARCUS? Are there any limits on the size of the map?
Yes, you can. Go on. Do you want me to take that one, Matt, or do you want to?
No. Please go ahead, Sam.
Yes, you can map with ARCUS. So again, ARCUS is the post-processing. So the data capture, the way that you capture your data, the way that you map, whether it's encoded or manually stitched, that still remains exactly the same. So once you've captured your data and saved that FMC file, it's at that point then you would apply your ARCUS. Now, of course, if you've got a relatively large area, you wouldn't need to apply ARCUS to the whole mapped area. If you wish, you could just focus it on one particular area where you suspect the floor to be, or where you can see the floor, and then you could just crop that data out and run ARCUS on the smaller area rather than doing it on the total area. Limits on the size of map, but again, the size of map that you encode, that's the limiting factor there is based on the RAM of your system. The bigger the map, the more data you're going to be saving, the more data you need to compute. So the size of the map, it's not a limitation of ARCUS, that's a limitation of your device when you're capturing your data.
Yeah, that's a really good point. And I think, it's we've talked about it before in other webinars and videos and obviously demonstrations, is that the Dolphycam 2 software saves all the data within the range. So if your part is 5 millimeters thick, but your range is set to 25 millimeters, you're going to be saving data from a lot of dead space. So efficiency in the setup is key as well. But yeah, that sort of allows us to segue a little bit into one of the other software that we have is called Data Snip. So Data Snip does exactly what Sam just alluded to there, is the fact that if you have a large mapped area, say 0.5 meter square, for example, and you have one defect, Data Snip allows you to extract that area into its own separate data file, so that every time you're opening it and processing it, you're not processing all of the data. You can then, of course, apply the ARCUS software to that extracted data, because when we're extracting data, we're extracting all of the A-scan data, not just an image, as it were. So, yeah, there are many tools, I guess, to that answer.
Thank you. So the next question is, does ARCUS need to be subscribed, or is it a free feature?
I'll take that one. No, it is not a free feature. This will be an additional tool to the Dolphycam 2 software suite. It will first be available as a licensed dongle. We are yet to, I think, settle on a final price. Sorry for not having that ready quite yet for this webinar, but there are a lot of factors that we have to take into account. But rather than making it fixed to a single PC, what we're going to do is it's going to be via a dongle that you plug into your computer. And that will then means that you have the freedom to be able to move it between instruments and between people as well. So yeah, so it will be a licensed software, and it will be in addition to the standard Dolphycam 2 software.
Great. And the final one I can see, and again, if anyone else has any questions, please just enter them in now, is how do you measure its improved accuracy?
Great question. Yeah, and a very valid question. So as with any new software that we release, we will always do POD studies. These are ongoing at the moment because we're aiming to do POD studies with the sort of core defect types that you find typically within composites. And these are going to be done against standards of known defect sizes in comparison too. So they are ongoing, and they will once they're completed, we'll be making them available to people. So yeah, they are currently in the process of being completed, and they're underway. Yeah.
Great, and that's that was actually all the questions that we had so far.
Super. Okay. Well, that takes us to 50 minutes, or 1 minute over. So I'd just like to extend our gratitude again for everybody who joined and came along and listened. Thank you very much. And I think now, Sam, we can close the webinar.
Right. Thank you, everyone.
Thank you, everyone. All the best.
Thanks. Take care.
Bye. Bye.